Very good morning, good afternoon, good evening to my dear friends who are taking this TQM2 lecture, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, welcome to this 12th lecture, which would basically be in the third week, which means you have completed already 5 lectures in the first week, another 5 in the second week, that is 10 completed. So, this is the second in the third week. So, we are discussing about different tests for the etching problem and how they can be framed, considering that main assumptions which I may be going back and forth, but do understand that the main assumptions being that the variance for the errors are independent on each other and they are not changing. So, they are not time dependent, because if that happens, obviously things go out of control. And we also consider the balanced problem, the unbalanced problem, in which the case the sample size is same for each and every treatment, it is different for different treatments. And we also propose the problems that how we can consider the null hypothesis where all the mean values are same, alternative hypothesis at least 2 of the mean values are different. We can consider that the variability are the same. In the alternative case, we can consider the variabilities are different, and based on that we consider that how we can use the t distribution. If you remember, t distribution is only to be used for the case when we are using the mean values, either the mean values or the difference of the mean values, whatever it is, and the underlying distribution we also always consider it to be normal. And the concept of chi-square and f distribution also came up, depending on whether it is less than type, greater than type, not equal to. Based on the fact we are only interested to study something to do with the standard deviation. So, f would be for the case when you are trying to find out the ratios of two standard deviation from two population, and the chi-square would be based on the fact that you are trying to understand something to the standard deviation of that population, giving some information from the population itself. And we also saw the degrees of freedom would change depending on what is the efficiency loss of the samples observations you take. You utilize it once, twice, thrice, so on and so forth, depending on what you want to find out, and then the tests were done. And we also saw that how the QQ plots could be used to utilize, how the box plots could be utilized in order to understand whether there is normality, whether there is non-normality, and all the subsequent topics. Again, I am mentioning the slides are fine, but best would be if you refer to the book. Maybe a little bit on the higher end the book is, but trust me, it is one of the classic books which can be utilized to study the concept of design of experiments. You can go slowly, you do not have to understand each and every topics for the actually the derivation of the formulas, but try to appreciate the end result of the formula which is being utilized, and how the results for the problems which are solved, how they can be utilized using the derived formulas or the theorems. So, considering the orthogonal and the combined orthogonal contrast. So, if you have treatments which is under control, 2 is another level 1 and 3 is under level 2. So, coefficient of the orthogonal contrast are given in the table. So, these values are consequently and respectively -2. I am going through the column -2, 1, 1, and the other values are 0, -1, 1. So, generally the method of contrast or orthogonal contrast is useful for what are called the pre-planned comparison. So, you are basically going to compare them according to some set procedures. That is, the contrast are specified prior to running the experiment and examining the data. So, obviously you have set the goals accordingly and done the experiment. Examining the data to select comparison of potential interest is often called data snooping, and you basically you check the data and what information you can get from this data. Comparing pair of treatment means, in many practical situations we wish to compare only pair of the means. Frequently we can determine which means differ by testing the difference between all pairs of treatment means. Thus, we are interested in contrast to form the difference of the means as mu I minus mu j, where I is not equal to j. So, say for example, if there are A such treatments, we would like to compare the difference of any 2 combinations of the means taken 2 at a time from this A set. Suppose that we are interested in comparing all pairs of treatment between means, that the null hypothesis then can be basically formulated as H suffix naught, which is the null hypothesis means mu suffix I is equal to mu suffix j, where I is not equal to j, and obviously the alternate hypothesis will be the complementary part. So, remember that the word I am complementary I am utilizing for the first time, but obviously you would have understood in this sense that whatever the H naught is, the total experiment or whatever achievement you can do, you are trying to divide into and apportion that into two sets. One would be the H naught, and obviously if you want to test the alternative hypothesis, it will be the complementary part. So this is the Tackies test. So suppose that following in an ANOVA in which we have rejected the null hypothesis of equal treatment, we wish to test all pair comparisons, which means in H naught it will be each of them are unequal, and H A, that means H mu I is not equal to mu j for I is equal to 1 to j, depending on whatever combinations you have. Minimum 1, obviously it will fail, that means you will support H A. More than that, obviously you will support H A. So Tackies procedure makes use of the distribution of the student's range test. So in the student's range test, what you want to find out is in the ratio it will be the maximum and the minimum. So you want to find out the difference between the max value and the min value, and in the denominator you will basically divide it. If you remember, if we go step back, watch when you are trying to basically find out the standard deviation of x bar n, which is the sample mean. So it's basically mean value was mu and variance was sigma square by n. So if you find out the transformation into z distribution, it will be x bar n minus mu divided by sigma by square root of n. So if you basically go into the denominator in this problem, it is basically square root of mean squared of the errors divided by n. So it makes a one-to-one significance based on what facts which you have already learned, and also the fact what is there in front of us. So where y bar max and y bar mean are the largest and the smallest sample means respectively out of a group of p sample means. So this appendix which you find in the book basically would have all the values of this case of q suffix a alpha. Alpha is basically the degrees of freedom concept which you are trying to understand. P is the sample means, and while f is the number of degrees of freedom. So obviously we can find out the different values of q corresponding to these three values, the parameters alpha, p and f, and the tables which is there, table 7 in Montgomery will give you all the values corresponding to this Tackies test. For equal sample sizes, Tackies test declares two means significantly different if the absolute value of the sample differences exceed the value of t value, which is given as here, where q suffix alpha in the bracket p comma f would basically be coming from the table, and then you will basically have the square root of mean squared error divided by n, which means basically something to do with the t table would be the capital T, Tackies test, not the small t which is the t distribution. You will use these values and test whether it is less than, greater than or not equal to. Based on that, you will either support H naught or basically reject H naught. So these are the values which are utilized. So obviously you will have f which is the degrees of freedom along the first column, and the values of p's are given on the topmost row, and the inner values are basically given as the Tackies values capital T with the corresponding alpha values. So alpha values can change, you will have different type of tables. So let us consider the Tackies test as an example. So to illustrate Tackies test, we use the data from the plasma etching example, where alpha considered is 0.05. So 1 minus alpha would be 1 minus 0.05. F is given as 16 degrees of freedom, because if you remember there were 20 observations, that means 5 into 4, and for each case you have to find out the mean. So how many such A's were there? A was 1, 2, 3, 4, which was corresponding to 160, 180, 200 and 220. Based on that you find out the total degrees of freedom would be 20 minus 4, which is 16. So appendix 7 in the table which we just considered, it will give a q value with the corresponding alpha is 0.05, value of p as 4, and p is basically the number of samples which you have, which was A, and 16 means the degrees of freedom. The value of q comes out to be 4.05. Therefore we can find out the capital T, which is the Tackies value, as 33.09. Thus any pairs of treatment average that differ in absolute value by more than 33.1 or 0.9, whatever it is, would imply that the corresponding pair of population means are significantly different. So what we have is that 4 treatment values are given. So when we find out the differences, these values are given, and the differences in the averages are given as 36.2, 70. I am not talking about the negative or the positive value, I am just giving the absolute value. 74.2, 155.8, 38, 119, 81. So, the start value which you see, so all of them are start, so that means they are greater than 33.09, whatever the values you find out using the tables and the Tackies capital T value. The start values indicate the pairs of means that are significantly different. Note that the Tackies procedure indicates that all pairs of means are different. Therefore, each power setting results as a mean rate, H rate is changing. So, which will mean that you have to basically understand the mean values for each etching depending on the treatment levels 160, 180, 200 and 220 are different. So, comparing treatments means with the controlled and which is the Dunnet test. In many experiments, one of the treatment is a control and the analysis is interested in comparing each of the other a one treatment mean with the control value. Thus, only a one comparisons are to be made. So, what are those? Suppose the treatment is in control and we wish to test the hypothesis, which is that, so they are a 1 to A, we keep the A fixed. So, the null hypothesis would be mu I. So, I is equal to 1, 2, 3, 4 till the second last one, which will be the A minus 1. So, say for example, you are considering 10 and the fifth you want to fix. So, obviously, you will try to compare the first to the fifth, second to the fifth, third to the fifth, fourth to the fifth, then 6 to the fifth, 7 to the fifth, 8 to the fifth, 9 to the fifth and 10 to the fifth. So, that is what is given. So, A value can change. So, here H naught is mu I is equal to mu A, and on the alternative hypothesis would be mu I is not equal to mu A. For each hypothesis we find out the compute the observed difference in the sample means, and those values are given as, so what they would be. So, you have to find out the averages. Average would be along the row, which means for sample 1, sample 2, sample 3, sample 4 and sample 5 for that etching example. So, that you will need to find out y bar I dot. So, that difference has to be found out with respect to y bar A dot, which is the fixed so called averages which you have. So, here if you remember and if you see it here it means I is changing from 1, 2, 3, 4 till A minus 1. So, the null hypothesis would be mu I is equal to mu A with respect to H naught. So, H naught was given like by mu I is equal to mu suffix A, and H A would be the complementary part. So, you will so the null hypothesis is rejected using the type 1 error rate of alpha. If you remember, I did mention that there are two type of errors, alpha and beta. In the case of hypothesis testing, we keep beta fixed at a certain level and then basically do our experiments with the concept of alpha. It can be done the other way round also, there is no problem. So, you find out the differences, mod of that is greater than the values which is given, which is d suffix alpha A minus 1 comma f is basically the total degrees of freedom, and A minus 1 would be the so called sample size, with the constant d suffix alpha A minus 1 comma f is given in the table 8. So, both the one sided and the two sided values are given. Note that alpha is the joint significance level associated with A minus 1 test, because A was the total number of etching. So, minus 1 because you are basically keeping one of them as fixed. To illustrate this Dunnet test, consider the experiment from example 3.1, which is the etching example. Treatments are 4 in number considered. So, A is 4, A minus 1 is 3, F is 16 because that is 20 minus 4, and Ni's because all of them are equal, they are 5. So, N1, N2, N3, N4 are all 5. So, at the 5% level we find out using table 8 the value of D with corresponding alphas and A minus 1 and F coming out to be 29.92. So, based on that fact, so we try to find out the differences. So, the differences as the observed differences are given where I am basically pointing my finger. So, these are they are without the negative or the positive sign, I am just giving the values. That is 155.8, 119 and 0.6 and 81.6. So, the note that all the differences are significant, thus we would conclude that all power settings are different from the controlled one which is given. So, you can basically change the controlled one, go to the first one control and basically compare the second, third, fourth with the first one. Then you basically can fix second, compare with first, third and fourth, you can do that experiment. So, you consider that if there's a workman working on some trying to manufacture some tie rod or trying to basically manufacture some gear, or you have some special jigs and fixtures which have been put on the sophisticated CNC machine, and you want to compare the output of that machine, keeping that as fixed with the other new machines which have been just purchased. So, you can do this type of experiments on Dunnet test and compare the variability or the difference in the means, and compare how those other production processes are going on with respect to the fixed one, where you have basically much control and where you are aware of the quality levels. So, the two-sided comparison values are given, which is the table 8 which we are talking. So, the A minus 1, which is the number of treatment means excluding the control ones, are given. So, you have basically 1, 2, 3. So, which is the second column, third column, fourth column, and the first column is the F, which is basically the degrees of freedom. So, if you remember, so degrees of freedom here it is 16, and if there A minus 1 value is 3. So, if you note it, even though I did not mention in tables 7, but I will try to basically highlight it. So, this 2.59 would be utilized as the D value and the calculations done correspondingly. So, now you want to determine the sample size. So, the next discussion would be determining the sample sizes. In any experiment design problems, a critical decision is the choice of the sample size, that is determining the number of replicates to run. So, generally the experiment is interested in determining small effects, more replications are required than if the experiment is interested to detecting large effects. So, you will basically use this. Here we discuss an approach this problem using the OC curve, the operating characteristic curves, which we did. If people have done this TQM1 course, we have considered that. So, an operating characteristic curve is a plot of the type 2 error probability of a statistical test for a particular sample size versus a parameter that reflects the extent to which the null hypothesis is false. So, these curves can be used to guide the experimenter to selecting the number of replicates, so that the design will be sensitive to important potential difference in the treatments, and you can basically take decisions accordingly. We consider the probability of type 2 error. So, type 2, if you remember type 1 and type 2, type 1 was error was given by alpha, and type 2 was basically given by the value of beta. So, type 2 error of the fixed effect model for the case of the equal sample size per treatment. So, here beta would basically be, because it is going in a complementary part, and if you remember the example which I gave of, like you are a banker and a manager and you want to basically disburse loans, obviously you have a cutoff points based on which you will decide whether you will want to give the loan and whether you want to not give the loan. So, any set of persons who have 60 points, credit points and above, you will give the loan, and any set of persons who have scores less than 60, you would deny the loan. So, obviously beta would be, if you consider the complementary part, and let me draw the diagram once again for the benefit. So, this was the line, you had two distributions, and I use, so technically those were the H naught and HAs. So, let me change the color to so this was the straight value. So, now you have the values, just give me 1 minute. So, this was the so called alpha and beta values we considered. Based on that, we did our analysis, or tried to basically give the rules accordingly. So, beta would be 1 minus probability of rejecting H naught when H naught is false, and obviously that will be counterpart of alpha. So, in this case you will basically have for the F test, it will be 1 minus probability of F naught being greater than that F under H naught would be greater than F alpha, or 1 minus alpha wherever less or greater depending on how you have framed the hypothesis. And A minus 1 would basically be the sample size, because one you are keeping fixed and the others you are trying to compare with the fixed one. So, in this case treatment 1 was the last one which is fixed, which is the 221, and the total degrees of freedom, as we already know, would be 4. I am repeating it, please excuse me, it will be basically 4 into 5 minus 4, which is 16, and based on the fact that H naught is false. because under H naught you will consider H naught to be true, under the alternative one it will be false. So, to evaluate probability statement of equation 3.43 as per the book, so mentioned earlier, we need to know the distribution of the test statistics F naught if the null hypothesis is false. It can be shown that if H is false, then F naught, which basically the ratio of mean square of the treatment by mean square of errors, is distributed in a non-central F distribution with a minus 1 and n minus 1 degrees of freedom and non-centrality parameters respectively. So, a minus 1 would basically be the degrees of freedom, and if the parameter value is basically delta. So, if delta is 0, the non-centrality values, the overall skewness would not be there. So, operating characteristic curves given in chart 5 in the appendix are used to evaluate the probability statements of related to the equation we have just discussed, and we will consider that the curve plots of the probability of type 2 errors are given against the parameter value of capital phi. So, where the capital phi is given by this equation of 3.44, which is basically the ratio of. Now, if you remember, tau was basically the difference between the average of the means minus the corresponding average to each and every treatment, which is basically mu I minus mu. So, obviously, there would be an error, and in one of the hypotheses we did frame it as tau is equal to 0, which is H naught, with respect to the null hypothesis where tau were not 0, or any one of them tau values were not 0. So, in the ratio we have in the numerator the sum of the tau values square, because you are considering basically intrinsically, even though I did not mention, we are considering the squared error loss to be true, because that gives us some implication of the concept of variance. If you are trying to basically minimize squared error loss, it gives us some implication that we are trying to basically minimize the variance, divided by. So, that would be the numerator will be multiplied by n, the sample size for each and every treatment, divided by A is basically the one which is the total number of such treatments which you have, into sigma square. If you remember, we are taking sigma square as basically the standard deviations, square of that will be sigma square, and we also consider the errors are independent of each other. So, the quantitative capital phi square is related to the non-centrality parameter delta. So, it has nothing to do with so called the capital phi, the small phi we saw, or many of you know in the case of normal distribution. So, curves are available for alpha is equal to 0.05, alpha is equal to 0.01 and so, and all these values, and a range of degrees of freedom for the numerator and denominator are given, and you can utilize those values accordingly. So, in using the OC curve, the experimenter must specify the parameter capital phi and the value of sigma square, so which is basically given by the experimenter, and depending on the data which you are utilizing. This is often difficult to do in practice. So, one way to determine capital phi is to choose the actual value of the treatment means for which you would try to basically like to reject a null hypothesis with high probability. Thus, if mu 1, mu 2, mu suffix 1, mu suffix 2 and so on and so forth till mu suffix a are the specified treatment means, we find tau i's as per the equation 3.48. So, these values are given. So, mu tau I would be mu I minus mu bar. Mu bar is basically being utilized as the best estimate for the average of the average from the population. We are using the sample to basically estimate the population average mean, and this mu bar is basically given by the sum of all the means divided by A, because there are such A treatments, which is the average of the individual treatment means. The estimate of sigma square may be available from prior experience, a previous experimental or preliminary test as suggested, or a judgment estimate can be made. So, when we are uncertain about the values of sigma square, sample size could be determined for a range of likely values of sigma square. To study each effect of these parameters, and required sample can be chosen before a final decision is making accordingly. A significant problem with this approach in using OC curves is that it is usually difficult to select a set of treatment means on which the sample size decision should be based. So, we are not certain what should be sample size, so it becomes difficult. An alternative approach is to select a sample size such that if the difference between any two treatment means exceed a specified value, the null hypothesis should be rejected. if the difference between any two treatment means is as large as d, so it can be utilized as the minimum value of sigma square, and that value is given by n into d square by 2 a sigma square. So, this remains the same. Because this is the minimum value of sigma square, the corresponding sample size obtained from the operating characteristic curve is a conservative value, that is, it provides a power at least as great as the specified by the experimenter. Discovering dispersion effects. So, you have focused on using the analysis of variance on related methods to determine which factor values or results in difference among the treatment or factor level means. So, it is customary to refer to these effects as location effects. So, we have considered the concept of difference on the means, considering something to do with the tau values being 0, consider something to do with sigma square as 0. So, I am talking about H naughts. So, obviously, H A's would be the alternative parts. We also considered that we are trying to keep any one of them comparison as fixed value and trying to compare the average means with that fixed value. So, for our example, we considered A, which is the last one as fixed, which is 220 volts or the wattage powers, and then we saw that how different type of test or Tackies test, T test, F test, chi-square test, Bartlett's test all could be utilized depending on the framework of the problem. So, if there were inequality of variances at different factor levels, we use transformation to stabilize them, the variance, in order to improve our inference on the location effects. So, in some problems, however, we are interested in discovering whether the different factor levels affect variability, that is, we are interested in discovering a potential dispersion effects, which would basically be may be a major concern later on. So, we want to take some corrective actions for that. This will occur whenever the standard deviation, variance, or some other measure of variability is used as a response value. To illustrate these ideas, let us consider the data as given, which results from a design experiment of an aluminum smelter. So, consider this. So, you have the data for the aluminum smelting process, you have the ratio of the control values which are given, which are the numbers are 1, 2, 3, 4, which is the first column in table 3.15. And the observations are 6 in number for each and every row. So, they start basically from 4.93 and go to 4.88. I am only leading the first and the last value for the rows. Similarly, you have in the fourth row, the values are 4.89 till the last value, which is 4.76, and the analysis of the variance, the test values are given. So, the ratio of the control algorithm, the errors and the total errors, total will obviously be the sum of them, are given as 6.166 for the ratio of the control, the errors are given by 1.872, and the sum is basically sum of both of these. The degrees of freedom are given, obviously degrees of freedom would also add up to be the 7. So, the ratio of the control algorithm degrees is 3, for the error is 20, the total is 23. The mean square values are given, which are corresponding to the first row for the value, which is a ratio of the control algorithm as 2.055 and as error being 0.094. F naught values are given as 21.96 and the p values considering to that experiment we find out, and depending on the level of significance, whatever it is there. So, discovering the dispersion effects, analysis of variance was performed to determine whether there is different ratio controls affecting the average of the cell voltages of the smelting process. This revealed that the ratio control algorithm had no location effects, that is, the changing in the ratio control algorithm does not change the average cell voltages. So, and then we can basically, I did not go into the example in details, but we have done that etching problem in details in different perspective in different angles. So, that will give you an idea that how those examples can be or informations can be utilized for solving such problems. So, with this I will end the 12th lecture and continue discussions of ANOVA and factorial design later on. And I wish any queries which have come up in the first two weeks, we would try our level best to answer them, and obviously the assignments you have all taken care of that and submitted the first and the second as per the norms or dates given, and we will continue the discussions for this TQM2 lecture further. Thank you very much. Have a nice day.